helicopter, and a package. We have a helicopter moving straight up with a constant velocity of 11 meters per second. When it's 150 meters above the ground level, the pilot drops a package. Ignore air resistance for this problem. First of all, find the position of the package relative to the ground and its velocity 5 seconds after it was dropped out of the helicopter. B, what is its maximum height? How long till it gets there? C, how long will it stay in the air? D, what will be the velocity of the package just before it strikes the ground? And then graph the following: position, velocity, and acceleration after the package is dropped. Find the position of the package relative to the ground and its velocity 5 seconds after it was dropped. We're going to use the second kinematics equation and the first kinematics equation for the velocity. Second, of course, is for the position. Even after the package is dropped, it initially keeps moving up with the velocity it had while in the helicopter. That's its v0. We're going to choose the up direction as positive. And we're allowed to use the kinematics equations here because the only acceleration once the package is dropped is due to gravity, which is a constant. A is minus g. So here's second kinematics. We put in our numbers. We start at 150 meters above the ground. An upward initial velocity due to the helicopter of 11 meters per second. And that's going to be effective for the 5 seconds that we're looking for right there. And then we add in the 1/2 at squared. And a in this case is negative 9.8. We do the math. And since we were talking about reference to the ground, we know that the package is now only 83 meters above the ground. Now we'd like to find the velocity 5 seconds after it hit the ground. Well, here we just have the first kinematics equation. We put in our initial velocity, add in the acceleration term, which is negative 9.8, 5 seconds. And the package is doing negative 38 meters per second, and the negative sign tells us that the package is on its way down here. We now want to find the maximum height reached by the package, and how long will it take to reach that height? We know that you reach a maximum height when your object has a 0 velocity. So since we want to find a displacement or a distance, and we know the acceleration, and we know our initial velocity, and right here, this is going to be our final velocity, or v, that's the third kinematics equation. So our final velocity is 0. And what do we put in now? We do a little algebra. Delta y is minus v0 squared over 2a. However, a is a negative g, so that gets rid of our negative sign, and we just have v0 squared over 2g. We plug the numbers in, and this is the change in height compared to our initial height. And this is our initial height here. So it goes up another 6.2 meters. So what would be the height above ground at that point? Well, it'd be 6.2 plus 150. And we just put the words here just to emphasize that's what we found. We found a delta y, not its absolute value above the ground. And reinforcing what we said on the previous page, we found the height above the point where the package was dropped. And that sounds funny, right? You dropped it, but we're talking about the height. But that is what happened because it had that initial velocity from the helicopter. So delta y is our y max minus where we started. We go ahead and move it around till we find y max. Our initial y was 150. We went up 6.2 meters. So the maximum height the package reached was 156.2 meters above the ground. We now want to find out how long it took to reach that height. Let's go to the first kinematics equation. And again, our final velocity will be 0 because your maximum height is where you momentarily start moving in the up direction and you now start heading down. So that will be v0 plus at. A is minus g. We plug in our numbers here, and it takes 1.1 seconds. So the package keeps rising for another 1.1 second after it's dropped out of the helicopter. How long will the package stay in the air? Let's go back to our second kinematics equation. And what's the status? When will it be on the ground? That's going to be when y is equal to 0, right? So it's in the air until y is equal to 0. So we put our numbers in here, substitute in, and we have a quadratic equation. So you can either use the quadratic formula or the solve function on your calculator, or go to one of any number of websites which will solve quadratic equations for you. Of course, you can't do that on the AP test, so you're limited to this or your calculator. We get two roots. We'll take the positive root because we're moving in positive time, and the package will take 6.8 seconds before it hits the ground. What will the velocity of the package be just before it strikes the ground? We'll go back to the first kinematics equation, and we'll take the time that it's in the air that we found from part C. So it's v0 minus gt. Here's our initial velocity. Here's our acceleration, minus 9.8. And here's how long the package is in the air from part C. And we find that the package has a velocity of negative 56 meters per second, which shows that it's heading down when it hits the ground, which of course makes sense and also rhymes a little bit. Now we're going to graph position, velocity, and acceleration after the package is dropped. We'll start with the hardest one. And again, if you're strategizing on an AP exam, probably start with acceleration. Because what is the acceleration? It's constant, isn't it? So you'll at least get those points. So you can either use the graphing function on your calculator, or what I did on this, of course you can't do this during the exam, I used this online website called graphfree.com, which is pretty cool, and it graphed that for me. But we're going to show you, okay, here's the equation. This is what I graphed, okay? I just input that, and it gave me this nice graph over here. And it kind of checks with what we said. The package would keep rising after it was dropped out of the helicopter, and then it's just free fall, which is a parabola. But let's look at the next slide to show how you could do it if you didn't use a calculator or a graphing software. We know it's going to be a parabola because of the t squared term in the equation, and also because we know it's in free fall. Okay, so that's t squared. We know that from previous work. And let's start sketching. We know that the package starts at 150. That gives us this point. We know it reaches a maximum height of 156 meters at 1.1 second. Because we've calculated that, so that gives us another point. And then we know it hits the ground, which is height 0, right down here, at 6.8 seconds. So we would just, knowing that it's a parabola, and this is the peak, we would just kind of sketch a curve through there, and that would be just fine. To graph the velocity, we know that the velocity increases linearly in free fall. And as a matter of fact, here's our equation. Right, v0 minus gt, where our initial velocity was 11 and g is negative 9.8. So we can just plot that. We know that the y-intercept for the velocity, or the velocity intercept, is 11 at time equals 0. So that's that point. We then know we have a slope of negative 9.8, which is how we can draw that line. Or we can just put a couple points. Right? We found our max height. We know the velocity is 0. So that happened at 1.1 second. That's right there. Okay, v equals 0 at max height, t equals 1.1 second. And we know it hits the ground at 6.8 seconds. So here's 6.8. And that will hit the ground. And we know the velocity is negative 56 meters per second. So you can see right over there. So we graphed this based on the numbers we got from the previous solution. Or you could have just gone ahead and graphed the straight line, of course. Just want to show what the straight line meant at the various points on the curve. And now for the gimme part of the problem. Graph the acceleration. Here you go. It's gravity, negative 9.8 meters per second squared. The only caution to be had on that one is if you have the graph like this, and you go ahead and draw a line here, make sure people know you're just not drawing another horizontal line, or that this might be your x-axis or time axis. So draw it a little thicker than any other line on the graph. Put an arrow, and I would strongly recommend just go a is equal to negative 9.8, and of course put the units down, meters per second squared, and draw kind of a little squiggly line there saying that's the curve I want you to look at.